we are going to create a new project in Code Composer Studio. When we open Code Composer Studio, we get this window. This is the main window in the software. It's the getting started window. Here we have to click new project. We click new project and we get this window. In this window here, we have to choose the target that we are going to work on. In this case, we're using a Tiba C processor, and we have to choose the family, or the board that we are using. In this case is 123GH6PM. We choose this. We have to give it a name, so we will give it a name called Blink. This is going to be our project's name, and it's going to be stored here. The location can vary depending on your computer. If you're using Windows, in my case I'm using Mac OS, so it is being stored in users and my workspace right here. We choose the compiler version. This is fine, the Texas Instrument, and here it gives us several options, which kind of project we want to create. We can create an empty project, no files. We can create an empty project with the main C file, or we can create an assembly only project. In this case, we want to choose with main, empty project, but give us a main.c file. We're going to click finish, and we get this window. We get the main.c file, which is what we requested. At the same time is empty file. It's got nothing but the main function. So in the C language, we must always have a main.c file, and inside that main.c file we must have a main function, and this is what we have here. And in this case, our main function is empty. It's not doing pretty much anything, just returning 0. So what we're going to do is we're going to build it. In every C program, the first thing we need to do is build and compile our software. So here, by clicking on this hammer, we click on this hammer right here. We're going to build the application. Here below we get an output right here. It says built-in file, invoking ARM compiler. So it is invoking the compiler and it's telling it, please compile this file for me. And here, building, we see blink.out. So all of this is basically the compiling process. The compiling process that Code Composer is doing by using the compiler and the linker provided by Texas Instrument. So once we click here in the binaries, we go in the binaries, we see a file blink.out. This is basically the output, the binary output of our program. This is the computer code, the ones and zeros that our computer is going to run. Here we have a very basic compilation diagram of how the compilation process is carried away. The compilation process is basically the program, the compiler takes the source file. In the case, in our example was the main.c file. It takes that file, it does pre-processing to that file. We're going to see that later, all the pre-processor. Step number 2, it does compile. The compiler runs, and it includes whatever we need to include, whatever macros we use. We're going to see macros also later on. It compiles and it translates that C file into assembly code. Assembly code is it's how programming was done in the earlier stages. People used assembly code instead of C code, but now we use C code. Now we use C code to program microcontrollers. So the compiler translates the C code into assembly code, and once we get the assembly code, the assembler translate that into machine code, and then finally the linking happens. The linking is basically any library that we're using, any external library, and also all the C files, all the object files that were generated, they have to be linked together to produce the binary file, the executable file. In our case, it was .out file, that is the binary file. So here we have a blink.out. This is the binary file. After going through all the process, compiling and then translating into assembly code, and then assembling, and then linking, finally produces a binary file. If we go to the binary folder, we're going to see that we have the blink.out file. That is our binary file. And now what we have to do is we have to flash the file in the microcontroller, and to do that we need to click here on the buck icon. So we click on the buck icon. When we click, we see this whole process here, and now when we see this this arrow here, that means our program is running. We can now either click run, or we can go step by step. If we go by step, we can see how the pointer goes forward, and here it's come to an end. We're gonna stop it right here. Right now it's not doing much. We're gonna get all this weird stuff because, well, it's ending, and of course it's returning to, it's returning to the main memory in the microcontroller. So what we're going to do now is we're going to add a little bit of code and play a little bit with our microcontroller. Now we're going to add a little bit of code, and what we're going to do now is we're going to learn how to declare a variable in C. To declare a variable in C, the most basic way is we need to define the data type. In this case, it's the type integer, and the name of the variable, we're gonna give it a name A, and then we have to assign a value. We're going to give a value. In this case, going to be, we're going to give it this value right here. So what we're doing is we're declaring the variable, and we're assigning a value to the variable. This is basically what we're doing here. Now let's compile this program, and let's debug. Let's flash it into the target, into the microcontroller. So here You can see the program is flashed. Now it's ready to run in the target. Here I got an extra window called disassembly. This is basically the translation from the C code into the assembly language. That's what we're looking at right here. To get this window, what you have to do is go here and in the menu, click view and disassembly. If you click here, you will get this this window here, which will give you the assembly code translation. All these symbols that you see here, sub W, mob W, this is called assembly language, and it's basically the translation of this assigning into assembly language. So let's go ahead and let's click here, step into. What step into does, it executes step by step our program. We click step into once. You see here it goes into the definition, and here in variables, this is called the watch. The watch, we can see we can watch our variables. You can see the name A, type integer, and right now it has a value of 691. This is a random value given by the compiler, and the location. So we click once more in the step into. Now we assigned it a value of 32,767. Now the variable A has this value, which is what we are assigned here. And remember how we said that the microcontroller has this bank of registers, and each register here, as you can see here, this is one location of memory, and in this location of memory it is storing these commands, and then in the next location of memory it's storing these commands, and so on. So it's basically storing the code, or the binary code, into memory, and each line of code of course is assigned into one line of memory. It's occupying one single register in memory. So here in this case, for the variable A, it's telling us the location of this variable. So we type here the location of this variable. Let's look for this address right here. You see here, this is the location of the variable, and we have the value 7ff. That is the variable A. That's the place where it is stored in memory. And we translate the translation of this is decimal value, translated into hexadecimal value is this value right here. It is the same value but in hexadecimal. Now let's look at another example. Let's declare the same variable, the same value, but with negative sign. Let's give it a negative sign. Let's compile. Let's flash into the target, and let's debug. Okay, here we are. Let's step into. Let's assign it a value. Here we have the value, the negative value that we are assigning, and let's look for this value in memory. We see now a totally different value. If we convert this, let's convert this into, this is the hexadecimal number. We convert it into binary. We see that we get all this weird notation, and even the decimal value does not match what we're given. Why is this? The answer to this is when we use a negative, what C does is it uses the last bit. This last bit is the sign. It's basically the sign of our number, our variable. In this case, we're using a negative variable, a negative value. So the 1 indicates that it's negative. And the rest of the bits right here, this is the value of the variable. But it is in something called complement of 2. The 2's complement is basically a method used in computer science. If you search this into Wikipedia, 2's complement, you will find a more comprehensive explanation. But basically this method is used to handle signed values and unsigned values. Here you can see in the table, these bits right here represent the 0 in the signed and unsigned. This bit right here, the 1, all zeros and just 1 represents 1 unsigned value and 1 signed value. Once we reach right here, as you can see here, we have reached this value. This is the sign. So when we're using signed integers, this will tell us that the number is negative when we're using signed. But if we're not using signed, we're using unsigned, this would basically tell us, this is 128. And the next one, we add 1 is 129. If we add 2, 130, and so on. But since we're using signed values, this would be negative 128. This one would be negative 127. So you can see it's going backwards until it reaches all ones. All ones in unsigned variables would be 255, but using sign would be 1. This is the sign. All ones, this is basically, if we translate this into complement, would be all zeros except the last one. This would be negative 1. So that's basically what we're getting here from this. This is the sign, and this is telling us this is the 2's complement. Basically this translation right here, is the 2 complement of the value that we are using, which is 2,767. Now that we know how C stores negative variables, negative integers, hopefully you don't have to worry about this. That's the beauty of using the C language for microcontrollers, that everything is handled by the compiler, by all the compiling process that we saw previously. You don't have to worry about translating into assembly language, into binary code. You don't have to worry about any of that. You just have to worry about, is it positive, is it negative, and it follows all the same arithmetic rules that you saw in school. 1 plus 1 equals 2, 1 minus 1 equals 0. It still applies like that. That's the beauty of using the C language. Now, one very important thing to understand is when we're using unsigned, let's here declare it as unsigned. I'm going to delete this. Let's declare 2 variables here, actually, A and B. So what we are going to do, unsigned basically means that we are not using the the sign. The bit will not represent the sign. The whole register will be used to represent our number in binary. So, for example, let's try. I'm gonna write here hexadecimal to decimal. Let's try this. FFF. For example, the number hexadecimal FFF, which is in decimal 65,535, and you can see complement is telling us -1, but right now we're interested in the unsigned, which is this value. In binary, basically represents 16 digits. So in our register, in the microcontroller register in memory, this is what we are going to see. We're going to see 1, 1, 1, 1, 1, 16 ones. This is the translation of this value into binary. So let's see, for example, how this works in our code. So now we're going to use in the variable a, we're gonna write this one, and in C, to write an hexadecimal value, what you have to do is write 0x and then f. This is basically the same value, but in hexadecimal. This is the hexadecimal of this. And you can corroborate it here in the conversion. You type FFF, convert it, and it will give you this value. In binary, it will give you this value. Okay, so let's go ahead, compile our project. Let's flash it in the board. And now let's step into assign the value to A. There you go. Assign the value to B. There you go. As you can see, both have the same value. Both have exactly the same value in hexadecimal. Let's go ahead and search for where the value is stored. A is stored in 1F8 and B is stored in 1FC right here. Both have the same values. Since we are using a 32-bit microcontroller, that means that every single one of these registers displays in memory, each one of those is 32-bit long. Our variable is 16-bit long. Here, he's giving us the conversion, you see, the hexadecimal and the decimal, octal, and binary. It's giving you the translation of this value in each of the different representations. So both of them have the same value, and since we have 32 bits, you can see that only half of the register is being used. The other half is 0. Why? Because we don't need, we only need half, we only need 16 bits. So you may wonder, can we use the full register? Yes. Yes, we can. And in order to do that, we're going to see how to do that. Okay, in order to do that, what we need to do is we need to occupy the full 32 bits by adding 1, 2, 3, 4. 4 more. And let's see how much is this in binary. We're gonna go here to our table converter, paste, convert, and now this is 32-bit long. You see, 32 bits. This is the value in decimal. This is the equivalent of this in decimal. So let's put that into the code. Let's put that into the code, this value right here. Let's compile. Let's flash it. And let's step into. Okay, yeah. So now if we look for the variables, as you can see, all the register is F. Everything is 1. Binary, everything, 32 bits, all ones. Why? Because now we have used the full let's say the full size of this data type. The data type unsigned int is interpreted as a 32-bit variable by the compiler. This is very important to understand when we are programming in C. Very important to understand when we are programming in C, because this is something that you're gonna find very often, that if you choose one data type and you want to do an operation with a different data type, sometimes you will get like these errors saying data type mismatch, data type is not the same. You're trying to do an operation with two different data types and it will give you an error. You have to be very careful to use the same data type. And you also have to know, especially in embedded development, you have to know the size of your integers. Later we're going to see how we can define each size, how we can define by size our own data types, because you might want to use only the 8 bits as we use of only 8 bits or 16 bits as we did previously, or you might want to use the 32 bits depending on what you're doing. Depending on the operation, you might need only 8 or 16 or 32 bits. There is a way to do that by declaring the variable with a specific data type, and we're going to see that later. So now that we know how the variables are stored in memory inside the microcontroller, how do we specify the size of the variable that we want to store? Well, turns out C provides with different data types that we can use to define the size of the variable that we're using. Let's say for example we want to declare an 8-bit variable. So we go ahead and declare unsigned char. Okay, so a is going to be an 8-bit variable, and then we're going to say B is going to be 16. Here what we have to do is declare as unsigned short. This will be a 16-bit variable, and in order to have an 32-bit, we need to declare it as long C, unsigned long C. So let's go ahead and we're gonna put, remember that in hexadecimal each F, by the way, in hexadecimal each F represents 4 bits. So this is the easiest way to populate with ones our variables, because we know that this is 4 bits of ones, so 8 bits would be ff, this is 8-bit long. And then for a 16-bit, guess what, is twice as much. This is 8, this is 16. And for a 32 bits is twice as the 16. So another 4, 1, 2, 3, 4. And now we have it's 8-bit, 16-bit, and 32-bit. Let's go ahead, build this, flash it. And now we are going to step into it. Okay, A equals ff 255, B fff, that's 60,535, and C, it's a really long number, but this is 32 bits. Now let's look for each of the variables in memory. We look for the C, is 1f8. As you can see, all populated in ones, 32 ones, 32 bits. And then the FC, this one, B, is 16 bit, that is half. You see here, these 4 F's represent the B variable, and the A is FA. But hold on a second here. Here we have, you see, we don't see FA. That's because FA is actually this part of the memory. So this is 32-bit long. Remember that? 32-bit long. As you can see, in each jump, we're jumping 2 and 2. We jump from 200 to 22. That's because each register is using two. Let's say each of the memory address is actually 16 bits long, but they are like joined here together. One FC and one FE, they are joined right here, both of them. So this part is the 1FE, which is the A variable. That's only 2 F's, as you can see right there. And in order to verify this, if you want to verify this, let's actually, I'm going to write here this, and then I'm going to put this as A, 3, D, E. Okay, this is to be able to identify each of the variables inside our inside the memory. This way we can understand how they are stored in memory. Now that we know how to define the size of our variables, let's take a look at something. Let's see what happens. For example, let's define the maximum value for each of them. Let's see what happens, for example, if A will become its value ff plus 1, B will become its current value plus 1, and C will become its current value plus 1. Let's see what happens if we do this. What happens if we go outside, we go beyond? This is already 8 bits contained in an 8-bit variable. What happens if we increase? We want to go beyond 8 bits. Let's find out. You can flash it, then let's step into each one. There we have our values. Let's find the variable. There they are. And you see here we know that this belongs to the variable b, and this belongs to the variable a. They are, for some reason, they are coupled together here in an FE and FC. They are here together, so we know that. Let's step into and let's see what happens to the variable a. Oh, you see, variable a has now become 0. Variable a has now become 0. This is called overflow. That means we already went through the maximum value, so we cannot count more than 255. Its value was 255, which is FF in hexadecimal. We cannot go beyond that value because this is defined as an 8-bit variable. So what will happen is we will restart from 0. Again, we restart from 0. Let's see what happened to variable b. Same thing. See, same thing. We now see how if we go beyond the size of the variable that we defined, we get an overflow. We will restart from 0. So if we do this operation once more, we add 1 again, this will go again 1 and 2 and 3 and 4 and so on until it reaches its maximum value. Depending on the size, these are the maximum values for each of the variables that we defined. So this is very important to know how we can define the variable size, how we can monitor, we can make sure that we don't overflow. What happens if we overflow? This is very important when we are programming in embedded development. We don't want to, especially when we are counting, when using counters, we are adding 1 and 1 every cycle. We don't want to restart again from 0. So we need to make sure that we don't go outside the limits of our variable size. Add another file to our project. Now we're going to see how we can add more files to our project. What we're going to do here is click here. We can go to file, I think here, new file, new. In this case, we're going to add a header. You can add source or header files. In this case, we're going to add header file. We're going to name it data types.h. And you're going to see the default C header template. Okay, finish. This is the default template that Code Composer gives us, and this is really nice. We should keep it as it is. This is called some guards, just to make sure that we don't include this file twice in our source. For now, what we need to focus on is how can we add this file, whatever we define here, how can we add it here? Well, we can do that by using this nomenclature include and the name of the file data types.h. And here what we're going to do is we're going to define our own data types. We can do this by doing type def. What I'm going to do is I'm going to do unsigned char, and we know that this is 8-bit. We're going to name it Wind8. So what we're doing is we're telling the C compiler define this data type for us, this data type, and it's going to be of data type unsigned char, which is 8-bit long. So we're going to do the same for the other one, unsigned short, and we're going to call it Wind16. This is a nice nomenclature because what it's telling us is the U is telling us is unsigned, int is an integer type, and 8 is 8 bits long. Here the same thing, unsigned, integer type, 16-bit long. We do the same for 32 bits, unsigned long, and this one is Win32. So now we have our data types, which are this one in red. They're highlighted in red for us. We can go ahead and use them. We're gonna go ahead and use them here. A is gonna be Wind8. This one is gonna be Wind16. This one is gonna be Win32 bits. Let's go ahead and build. Flash it on the board. And let's step into it. Okay. You see here, unsigned char. A is unsigned char, B is unsigned short, and C is unsigned long, which is the data types that we defined here. We are basically telling when the compiler is compiling this, what it's doing is it tries to find this. What does this mean? So it searches here in the header file, searches here, and it finds the symbol here. Okay, so this is a type definition by the user. And what is the type that is defining? Unsigned char. Okay, so what it does is replaces this Wind8 with unsigned char. That is basically what it does. It replaces this with whatever we define in there. And by doing this include, here we just type the name of the file. Here we're telling it, please include this other file here, so you can see my definitions. Now I am able to define my own data types. I'm able to do exactly the same thing. I'm able to add and overflow my variables. Everything is working fine.